Today, let's dive deep into studying the origins of the universe. In order to be able to understand its origins, then in turn, discover our true origins. Let's do so by recreating the scientific inquiry by looking into cosmology, and then study the Big Bang Theory, cosmic inflation, and the formation of galaxies and stars. Using key books, papers on astrophysics and cosmology, focusing on the works of renown, research experts, and the highly recognized works. These resources are celebrated for the scientific rigor and aims to present information based on empirical evidence and theoretical analysis, minimizing bias. Let us begin by examining and reviewing one such book, The First 3 Minutes. A Modern View of the Origins of the Universe by Steven Weinberg. This classic book by Nobel laureate Steven Weinberg provides a detailed account of the first 3 minutes after the Big Bang, explaining the information of the universe with clarity and precision. Join us on part 1 of this video review book review series. To find out why we recommend this particular book, The First 3 Minutes. A Modern View of the Origins of the Universe by Steven Weinberg.
Steven Weinberg's The First 3 Minutes, A Modern View of the Origin of the Universe. Context or contents within the book. Introduction: the giant and the cow, the expansion of the universe, the cosmic microwave radiation background, recipe for a hot universe, the first 3 minutes, a historical diversion, the first 100th second, epilogue, the prospect ahead. We found this in the public domain, public access, so no copyright infringement was intentional, and we bring it to all as part of this video review series for educational purposes alone. Contents: epilogue, afterword tables and glossary included. Preface: this book grew out of a talk the author gave at the dedication of the Undergraduate Science Center at Harvard in November 1973. Irwin Gleick, president and publisher of Basic Books, heard of this talk from a mutual friend, Daniel Bell, and urged the author to turn it into a book. At first, the author was not enthusiastic about the idea. Although he had done small bits of research in cosmology from time to time, his work had been much more concerned with the physics of the very small, the theory of elementary particles. Also, elementary particle physics has been extraordinarily lively in the last few years, prior to this book being written, published and printed. And the author had been spending too much time away from it, writing non-technical articles for various magazines. He wanted very much to return full-time to his natural habitat, the physical review. However, the author found that he could not stop thinking about the idea of a book on the early universe. What could be more interesting than the problem of Genesis? Also, it is in the early universe, especially the first 100th of a second, that the problems of the theory of elementary particles come together with the problems of cosmology. Above all, this is a good time, or was a good time, to write about the early universe. In just the last decade or so, a detailed theory of the course of events in the early universe had become widely accepted as a standard model. It is a remarkable thing to be able to say just what the universe was like at the end of the first second, or the first minute, or the first year. To a physicist, the exhilarating thing is to be able to work things out numerically, to be able to say that at such and such a time the temperature and density and chemical composition of the universe had such and such values. True, we are not absolutely certain about all this, but it is exciting that we are now able to speak of such things with any confidence at all. It was this excitement that the author wanted to convey to the reader. He felt that he had better say for what reader this book is intended. He had written for one who was willing to puzzle through some detailed arguments, but who was not at home in either mathematics or physics. Although the author felt he must introduce some fairly complicated scientific ideas, no mathematics is used in the body of the book beyond arithmetic, and little or no knowledge of physics or astronomy is assumed in advance. The author had tried to be careful to define scientific terms when they are first used, and in addition, he supplied a glossary of physical and astronomical terms, page 165. Wherever possible, he had also written numbers like 100,000 million in English, rather than use the more convenient scientific notation 10 to the power of 11. However, this does not mean that the author had tried to write an easy book. When a lawyer writes for the general public, he assumes that they do not know law, French, or the rule against perpetuities. But he does not think the worst of them for it, and he does not condescend to them. The author wanted to return the compliment. He pictured the reader as a smart old attorney who does not speak his language, but who expects, nonetheless, to hear some convincing arguments before he makes up his mind. For the reader who does want to see some of the calculations that underlie the arguments of this book, the author has prepared a mathematical supplement which follows the body of the book, page 175. The level of mathematics used here would make these notes accessible to anyone with an undergraduate concentration in any physical science or mathematics. Fortunately, the most important calculations in cosmology are rather simple. It is only here and there that the finer points of general relativity or nuclear physics come into play. Readers who want to pursue the subject on a more technical level will find several advanced treatises, including the author's own, listed under suggestions for further reading, page 189. The author felt that he should also make clear what subject he was intending this book to cover. It is definitely not a book about all aspects of cosmology. There is a classic part of the subject which has to do mostly with the large-scale structure of the present universe. The debate over the extragalactic nature of the spiral nebulae, the discovery of the redshifts of distant galaxies, and the dependence on distance, the general relativistic cosmological models of Einstein, de Sitter, Lemaître, and Friedman, and so on. This part of cosmology has been described very well in a number of distinguished books, and the author did not intend to give another full account of it here within this book. The present book is concerned with the early universe, and in particular with the new understanding of the early universe that has grown out of the discovery of the cosmic microwave radiation background in 1965. Of course, the theory of the expansion of the universe is an essential ingredient in our present view of the early universe. So the author has been compelled, or was compelled in chapter 2, to provide a brief introduction to the more classic aspects of cosmology. He strongly believes that this chapter should provide an adequate background, even for the reader completely unfamiliar with cosmology, to understand the recent developments in the theory of the early universe with which the rest of the book is concerned. However, the reader who wants a thorough introduction to the older parts of cosmology is urged to consult the books listed under suggestions for further reading. On the other hand, the author had not been able to find any coherent historical account of the recent developments in cosmology. He therefore was obliged to do a little digging himself, particularly with regard to the fascinating question of why there was no search for the cosmic microwave radiation background long before 1965. This is discussed in chapter 6. This is not to say that the author regarded this book as a definitive history of these developments. He had far too much respect for the effort and attention to detail needed in the history of science to have any illusions on that score. Rather, he would be happy if a real historian of science would use this book as a starting point. Note, a real historian of science, and write an adequate history of the last 30 years of cosmological research. And then he goes on to show his gratitude to Erwin Gleitz, Farrell Phillips of Basic Books with valuable suggestions preparing his manuscript for publication. He's also been helped by others, so he gives his thanks there, his reasons and his thanks there. Stephen Weinberg, Cambridge, Massachusetts, USA, July 1976. Introduction: The Giant and the Cow. The origin of the universe is explained in the Younger Edda, a collection of Norse myths compiled around 1220 by the Icelandic magnate Snorri Sturluson. In the beginning, says the Edda, there was nothing at all. Earth was not found, nor heaven above. A yawning gap there was, but grass nowhere. To the north and south of nothing lay regions of frost and fire, Niflheim and Muspelheim. The heat from Muspelheim melted some of the frost from Niflheim, and from the liquid drops there grew a giant, Ymir. What did Ymir eat? It seems there was also a cow, Audhumla. And what did she eat? Well, there was also some salt, and so on. The author must not offend religious sensibilities, even Viking religious sensibilities, he felt, but he thought it was fair to say that this is not a very satisfying picture of the origin of the universe. Even leaving aside all objections to hearsay evidence, the story raises as many problems as it answers, and each answer requires a new complication in the initial conditions. We are not able merely to smile at the Edda and forswear all cosmological speculation. The urge to trace the history of the universe back to its beginnings is irresistible. From the start of modern science in the 16th and 17th centuries, physicists and astronomers have returned again and again to the problem of the origin of the universe. However, an aura of the distributable always surrounded such research. The author remembers that during the time that he was a student and then began his own research on other problems in the 1950s, the study of the early universe was widely regarded as not the sort of thing to which a respectable scientist would devote his time, nor was this judgment unreasonable. Throughout most of the history of modern physics and astronomy, there simply has not existed an adequate observational and theoretical foundation on which to build a history of the early universe. Now, in just the past decade, or of late, all this has changed. A theory of the early universe has become so widely accepted that astronomers often call it the standard model. It is more or less the same as what is sometimes called the Big Bang Theory, but supplemented with a much more specific recipe for the contents of the universe. This theory of the early universe is the subject of this book. To help see where we are going, it may be useful to start with a summary of the history of the early universe as presently understood in the standard model. This is only a brief run-through. Succeeding chapters will explain the details of this history and our reasons for believing any of it. In the beginning there was an explosion, not an explosion like those familiar on Earth, starting from a definite centre and spreading out to engulf more and more of the circumambient air, but an explosion which occurred simultaneously everywhere, filling all space from the beginning, with every particle of matter rushing apart from every other particle. All space in this context may mean either all of an infinite universe or all of a finite universe which curves back on itself like the surface of a sphere. Neither possibility is easy to comprehend or understand, but this will not get in our way. It matters hardly at all in the early universe whether space is finite or infinite. At about 100th of a second, the earliest time about which we can speak with any confidence, the temperature of the universe was about 100,000 million, or 10 to the power of 11, degrees centigrade. This is much hotter than in the centre of even the hottest star. So hot, in fact, that none of the components of ordinary matter, molecules or atoms, or even the nuclei of atoms, could have held together. Instead, the matter rushing apart in this explosion consisted of various types of the so-called elementary particles, which are the subject of modern high-energy nuclear physics. Within this book, we will encounter these particles again and again. For the present, it will be enough to name the ones that were most abundant in the early universe and leave more detailed explanations for chapter 3 and 4. One type of particle that was present in large numbers is the electron, the negatively charged particle that flows through wires and electric currents and makes up the outer parts of all atoms and molecules in the present universe. Another type of particle that was abundant at early times is the positron, a positively charged particle with precisely the same mass as the electron. In the present universe, positrons are found only in high-energy laboratories, some kind of radioactivity, and violent astronomical phenomena like cosmic rays and supernovas. But in the early universe, the number of positrons was almost exactly equal to the number of electrons. In addition to electrons and positrons, there were roughly similar numbers of various kinds of neutrinos, ghostly particles with no mass or electric charge whatever. Finally, the universe was filled with light. This does not have to be treated separately from the particles. The quantum theory tells us that light consists of particles of zero mass and zero electrical charge, known as photons. Each time an atom in the filament of a light bulb changes from a state of high energy to one of low energy, one photon is emitted. There are so many photons coming out of a light bulb that they seem to blend together in a continuous stream of light, but a photoelectric cell can count individual photons one by one. Every photon carries a definite amount of energy and momentum depending on the wavelength of the light. To describe the light that filled the early universe, we could say that the number and the average energy of the photons was about the same as for electrons or positrons or neutrinos. These particles, electrons, positrons, neutrinos, photons were continually being created out of pure energy and then after short lives being annihilated again. The number therefore was not preordained but fixed, steered by a balance between process of creation and annihilation. From this balance we can infer that the density of this cosmic soup at a temperature of 100,000 million degrees was about 4,000 million, 4 times 10 to the power of 9, times that of water. There was also a small contamination of heavier particles, protons and neutrons, which in the present world form the constituents of atomic nuclei. Protons are positively charged, neutrons are slightly heavier and electrically neutral. The proportions were roughly 1 proton and 1 neutron for every 1,000 million electrons or positrons or neutrinos or photons. This number, 1,000 million photons per nuclear particle, is the crucial quantity that had to be taken from observation in order to work out the standard model of the universe. The discovery of the cosmic radiation background, discussed in chapter 3, was in effect a measurement of this number. As the explosion continued, the temperature dropped, reaching 30,000 million, 3 times 10 to the power of 10, degrees centigrade after about 1/10 of a second, 10,000 million degrees after about 1 second, and 3,000 million degrees after about 14 seconds. This was cool enough so that the electrons and positrons began to annihilate faster than they could be recreated out of the photons and neutrinos. The energy released in this annihilation of matter temporarily showed the rate at which the universe cooled, but the temperature continued to drop, finally reaching 1,000 million degrees at the end of the first 3 minutes. It was then cool enough for the protons and neutrons to begin to form into complex nuclei, starting with the nucleus of heavy hydrogen or deuterium, which consists of 1 proton and 1 neutron. The density was still high enough, a little less than that of water, so that these light nuclei were able rapidly to assemble themselves into the most stable light nucleus, that of helium, consisting of 2 protons and 2 neutrons. At the end of the first 3 minutes, the contents of the universe were mostly in the form of light, neutrinos, and antineutrinos. There was still a small amount of nuclear material, now consisting of about 73% hydrogen and 27% helium, and an equally small number of electrons, left over from the era of electron-positron annihilation. This matter continued to rush apart, becoming steadily cooler and less dense. Much later, after a few 100,000 years, it would become cool enough for electrons to join with nuclei to form atoms of hydrogen and helium. The resulting gas would begin under the influence of gravitation to form clumps, which would ultimately condense to form the galaxies and stars of the present universe. However, the ingredients with which the stars would begin their life would be just those prepared in the first 3 minutes. The standard model sketched above is not the most satisfying theory imaginable of the origin of the universe. Just as in the Younger Era, there is an embarrassing vagueness about the very beginning, the first hundredth of a second or so. Also, there is the unwelcome necessity of fixing initial conditions, especially the initial 1,000 million to 1 ratio of photons to nuclear particles. We would prefer a greater sense of logical inevitability in the theory. For example, one alternative theory that seems philosophically far more attractive is the so-called steady-state model. In this theory, proposed in the late 1940s by Herman Bondi, Thomas Gold, and in a somewhat different formulation, Fred Hoyle, the universe has always been just about the same as it is now. As it expands, new matter is continually created to fill up the gaps between the galaxies. Potentially all questions about why the universe is the way it is can be answered in this theory by showing that it is because that is the only way it can stay the same. The problem of the early universe is vanished. There was no early universe. How then did we come to the standard model? And how has it supplanted other theories, like the steady-state model? It is a tribute to the essential objectivity of modern astrophysics that this consensus has been brought about, not by shifts in philosophical preferences or by the influence of astrophysical mandarins, but by the pressure of empirical data. The next 2 chapters in this book will describe the 2 great clues furnished by astronomical observation, which have led us to the standard model, the discoveries of the recession of distant galaxies, and of a weak radio static filling the universe. This is a rich story for the historian of science, filled with false starts, missed opportunities, theoretical preconceptions, and the play of personalities. Following the survey of observational cosmology, the author would try to put the pieces of data together to make a coherent picture of physical conditions in the early universe. This would put us in a position to go back over the first 3 minutes in greater detail. A cinematic treatment seems appropriate, frame by frame. We will watch the universe expand and cool and cook. We will also try to look a little way into an era that is still clothed in mystery, the first hundredth of a second, and what went before. Can we really be sure of the standard model? Will new discoveries overthrow it and replace the present standard model with some other cosmogony, or even revive the steady-state model? Perhaps. The author cannot deny a feeling, or you could not deny a feeling of unreality in writing about the first 3 minutes as if we really know what we're talking about. However, even if it is eventually supplanted or replaced, the standard model would have played a role of great value in the history of cosmology. It is now respectable, though only in the last decade or so, to test theoretical ideas in physics or astrophysics by working out their consequences in the context of the standard model. It is also common practice to use the standard model as a theoretical basis or foundation for justifying programs of astronomical observation. Thus, the standard model provides an essential common language which allows theorists and observers to appreciate what each other is doing. If someday the standard model is replaced by a better theory, it will probably be because of observations or calculations that drew their motivation from the standard model. In the last chapter of this book, the author will say a bit about the future of the universe it may go on expanding forever, getting colder, emptier and deader. Alternatively, it may recontract, breaking up the galaxies and stars and atoms and atomic nuclei back into their constituents. All the problems we faced in understanding the first 3 minutes would then arise again in predicting the course of events in the last 3 minutes. Chapter 2. The expansion of the universe. A look at the night sky gives a powerful impression of a changeless universe. True, clouds drift across the moon, the sky rotates around the polar star, and over longer times the moon itself waxes and wanes, and the moon and planets move against the background of stars. But we know that these are merely local phenomena caused by motions within our solar system. Beyond the planets, the stars seem motionless. Of course, the stars do move at speeds ranging up to a few hundred kilometres per second, so in a year a fast star might travel 10,000 million kilometres or so. This is 1,000 times less than the distance to even the closest stars, so the apparent position in the sky changes very slowly. For instance, the relative fast star known as Barnard's star is at a distance of about 56 million kilometres. It moves across the line of sight at about 89 kilometres per second, or 2.8 thousand million kilometres per year, and in consequence its apparent position shifts in 1 year by an angle of 0.0029 degrees. Astronomers call the shift in the apparent position of nearby stars in the sky a proper motion. The apparent positions in the sky of the more distant stars change so slowly that the proper motion cannot be detected with even the most patient observation. We are going to see here that this impression of changelessness is illusory. The observations that we will discuss in this chapter reveal that the universe is in a state of violent explosion, in which the great islands of stars known as galaxies are rushing apart at speeds approaching the speed of light. Further, we can extrapolate this explosion backward in time and conclude that all the galaxies must have been much closer at the same time in the past. So close, in fact, that neither galaxies nor stars nor even atoms or atomic nuclei could have had a separate existence. This is the era we call the early universe, which serves as the subject of this book. Our knowledge of the expansion of the universe rests entirely on the fact that astronomers are able to measure the motion of a luminous body in a direction directly along the line of sight much more accurately than they can measure its motion at right angles to the line of sight. The technique makes use of a familiar property of any sort of wave motion known as the Doppler effect. When we observe a sound or light wave from a source at rest, the time between the arrival of wave crests at our instruments is the same as the time between crests as they leave the source. On the other hand, if the source is moving away from us, the time between arrivals of successive wave crests is increased over the time between their departure from the source, because each crest has a little farther to go on its journey to us than a crest before. The time between crests is just the wavelength divided by the speed of the wave. So a wave sent out by a source moving away from us will appear to have a longer wavelength than if the source were at rest. Specifically, the fractional increase in the wavelength is given by the ratio of the speed of the wave source to the speed of the wave itself, as shown in mathematical note 1, page 175. Similarly, if the source is moving towards us, the time between arrivals of wave crest is decreased because each successive crest has a shorter distance to go, and the wave appears to have a shorter wavelength. It is just as if a travelling salesman were to send a letter home regularly once a week during his travels while he is travelling away from home. Each successive letter will have a little farther to go than the one before, so his letters will arrive a little more than a week apart. On the homeward leg of his journey, each successive letter will have a shorter distance to travel, so they will arrive more frequently than once a week. It is easy these days to observe the Doppler effect on sound waves. Just go out to the edge of a highway and notice that the engine of a fast automobile sounds higher pitched, i.e. a shorter wavelength, when the auto is approaching than when it is going away. The effect was apparently first pointed out for both light and sound waves by Johann Christian Doppler, professor of mathematics at the Realschule in Prague in 1842. The Doppler effect for sound waves was tested by the Dutch meteorologist Christopher Heinrich Dietrich Weisbauer in an enduring experiment in 1845 as the moving source of sound. He used an orchestra of trumpeters standing in an open car of a railroad train whizzing through the Dutch countryside near Utrecht. Doppler thought that his effect might explain the different colours of stars. The light from stars that happened to be moving away from the Earth would be shifted towards longer wavelengths. And since red light has a wavelength longer than the average wavelength for visible sight, such a star might appear redder than average. Similarly, light from stars that happen to be moving towards the Earth would be shifted towards shorter wavelengths, so the star might appear unusually blue. It was soon pointed out by Weisbauer and others that the Doppler effect has essentially nothing to do with the colour of a star. It is true that the blue light from a receding star is shifted towards the red, but at the same time, some of the star's normally invisible ultraviolet light is shifted into the blue part of the visible spectrum, so the overall colour hardly changes. Stars have different colours chiefly because they have different surface temperatures. However, the Doppler effect did begin to be of enormous importance to astronomy in 1868 when it was applied to the study of individual spectral lines. It had been discovered years earlier by the Munich optician Joseph Fraunhofer in 1814 to 15 that when light from the sun is allowed to pass through a slit and then through a glass prism, the resulting spectrum of colours is crossed with hundreds of dark lines, each one an image of the slit. A few of these lines had been noticed even earlier by William Hyde Wollaston in 1802, but were not carefully studied at that time. The dark lines were always found at the same colours, each corresponding to a definite wavelength of light. The same dark spectral lines were also found by Fraunhofer in the same positions in the spectrum of the moon and the brighter stars. It was soon realised that these dark lines are produced by the selective absorption of light of certain definite wavelengths as the light passes from the hot surface of a star through its cooler outer atmosphere. Each line is due to the absorption of light by a specific chemical element, so it became possible to determine that the elements of the sun, such as sodium, we know that is salt, iron, magnesium, calcium and chromium, are the same as those found on Earth. Today we know that the wavelengths of the dark lines are just those for which a photon of that wavelength would have precisely the right energy to raise the atom from a state of lower energy to one of its excited states. In 1868, Sir William Huggins was able to show that the dark lines in the spectra of some of the brighter stars are shifted slightly to the red or the blue from their normal positions in the spectrum of the Sun. He correctly interpreted this as a Doppler shift due to the motion of the star away from or towards the Earth. For instance, the wavelength of every dark line in the spectrum of the star Capella is longer than the wavelength of the corresponding dark line in the spectrum of the Sun by 0.01%. This shift to the red indicates that Capella is receding from us at 0.01% of the speed of light, or 30 kilometers per second. The Doppler effect was used in the following decades to discover the velocities of solar prominences, of double stars, and of the rings of Saturn. The measurement of velocities by the observation of Doppler shifts is an intrinsically accurate technique because the wavelengths of spectral lines can be measured with very great precision. It is not unusual to find wavelengths given in tables to 8 significant figures. Also, the technique preserves its accuracy whatever the distance of the light source, provided only that there is enough light to pick up spectral lines against the radiation of the night sky. It is through use of the Doppler effect that we know the typical values of stellar velocities referred to at the beginning of this chapter. The Doppler effect also gives us a clue to the distance of nearby stars. If we guess something about a star's direction of motion, then the Doppler shift gives us its speed across as well as along our line of sight. So measurement of the star's apparent motion across the celestial sphere tells us how far away it is. But the Doppler effect began to give results of cosmological importance only when astronomers began to study the spectra of objects at a much greater distance than the visible stars. The author thought he only had to say a bit about the discovery of those objects, and he come back to the Doppler effect. He started this chapter with a look at the night sky. In addition to the moon, planets and stars, there are two other visible objects of greater cosmological importance that the author might have mentioned, or previously mentioned. One of these is so conspicuous and brilliant that it is sometimes visible even through the haze of a city's night sky. It is the band of light stretching in a great circle across the celestial sphere and known from ancient times as the Milky Way. In 1750, the English instrument maker Thomas Wright published a remarkable book, Original Theory or New Hypothesis of the Universe, in which he suggested that the stars lie in a flat slab, a grindstone of finite thickness, but extending to a great distance in all directions in the plane of the slab. The solar system lies within the slab, so naturally we see much more light when we look out from the Earth along the plane of the slab than when we look in any other direction. This is what we see as the Milky Way. Wright's theory has long since been confirmed. It is now thought that the Milky Way consists of a flat disk of stars with a diameter of 80,000 light years and a thickness of 6,000 light years. It also possesses a spherical halo of stars with a diameter of almost 100,000 light years. The total mass is usually estimated as about 100,000 million solar masses, but some astronomers think there may be a good deal more mass in an extended halo. The solar system is some 30,000 light years from the centre of the disk and slightly north of the central plane of the disk. The disk rotates with speeds ranging up to about 250 kilometers per second and exhibits giant spiral arms. Although a glorious sight, if only we could see it from outside. The whole system is usually now called the Galaxy. We're taking a larger view, our Galaxy. The other of the cosmologically interesting features of the night sky is much less obvious than the Milky Way. In the constellation Andromeda, there is a hazy patch, not easy to see, but clearly visible on a good night if you know where to look for it. The first written mention of this object appears to be a listing in the Book of Fixed Stars, compiled in AD 964 by the Persian astronomer Abdurrahman al-Sufi. He described it as a little cloud. After telescopes became available, more and more such extended objects were discovered, and astronomers in the 7th and 18th centuries found that these objects were getting in the way of the search for things that seemed really interesting, the comets. In order to provide a convenient list of objects not to look at while hunting for comets, Charles Messier in 1781 published a celebrated catalogue, nebulae and star clusters. Astronomers still refer to the 103 objects in this catalogue by the Messier numbers. Thus, the Andromeda Nebula is M31, the Crab Nebula is M1, and so on. Even in Messier's time, it was clear that these extended objects are not all the same. Some are obviously clusters of stars, like the Pleiades, M45. Others are irregular clouds of glowing gas, often coloured and often associated with one or more stars, like the giant nebula in Orion, M42. Today, we know that objects of these types are within our galaxy, and they need not concern us further here with this book. However, about a third of the objects in Messier's catalogue were white nebulae of a fairly regular elliptical shape, of which the most prominent was the Andromeda Nebula, M31. As telescopes improved, thousands more of these were found, and by the end of the 19th century, spiral arms had been identified, and some include M31 and M33. However, the best telescopes of the 18th and 19th centuries were unable to resolve the elliptical or spiral nebulae into stars, and their nature remained in doubt. It seems to have been Immanuel Kant who first proposed that some of the nebulae are galaxies like our own. Picking up Wright's theory of the Milky Way, Kant in 1755, in his Universal Natural History and Theory of the Heavens, suggested that nebulae, or rather a species of them, are really circular disks, about the same size and shape as our own galaxy. They appear elliptical because most of them are viewed at a slant, and of course they are faint because they are so far away. The idea of a universe filled with galaxies like our own became widely, though by no means universally accepted, by the beginning of the 19th century. However, it remained an open possibility that these elliptical and spiral nebulae might prove to be mere clouds within our own galaxy, like other objects in Messier's catalogue. One great source of confusion was the observation of exploding stars in some of the spiral nebulae. If these nebulae were really independent galaxies, too far away for us to pick out individual stars, then the explosions would have to be incredibly powerful to be so bright at such a great distance. In this connection, the author cannot resist quoting one example of 19th century scientific prose at its ripest. Writing in 1893, the English historian of astronomy, Agnes Mary Clerk remarked, "The well-known nebula in Andromeda and the great spiral in Canes Venatici are among the more remarkable of those giving a continuous spectrum, and as a general rule, the emissions of all such nebulae as present the appearance of star clusters grown misty through excessive distance are of the same kind. It would, however, be eminently rash to conclude these that they are really aggregations of such sun-like bodies. The improbability of such an inference has been greatly enhanced by the occurrence, at an interval of a quarter of a century, of stellar outbursts in two of them. For it is practically certain that, however distant the nebulae, the stars were equally remote. Hence, if the constituent particles of the former be suns, the incomparably vaster orbs by which their feeble light was well nigh liberated must, as was argued by Mr. Proctor, have been on a scale of magnitude such as the imagination recoils from contemplating. Today we know that these stellar outbursts were indeed on a scale of magnitude such as the imagination recoils from contemplating. They were supernovas, explosions in which one star approaches the luminosity of a whole galaxy, but this was not known in 1893. The question of the nature of the spiral and elliptical nebulae cannot be settled without some reliable method of determining how far away they are. Such a yardstick was at last discovered after the completion of the 100 telescope at Mount Wilson near Los Angeles. In 1920, Edwin Hubble was for the first time able to resolve the Andromeda Nebula into separate stars. He found that spiral arms included a few bright variable stars with the same sort of periodic variations of luminosity as well as was already familiar for a class of stars in a galaxy known as the Cepheid variables. The reason this was so important was that in the preceding decade, the work of Henrietta Swan Leavitt and Harlow Shapley of the Harvard College Observatory had provided a tight relation between the observed periods of variation of the Cepheids and the absolute luminosities. Absolute luminosity is the total radiant power emitted by an astronomical object in all directions. Apparent luminosity is the radiant power received by us in each square centimetre of our telescope mirror. It is the apparent rather than the absolute luminosity that determines the subjective degree of brightness in astronomical objects. Of course, the apparent luminosity depends not only on the absolute luminosity, but also on the distance. Thus, knowing both the absolute and the apparent luminosities of an astronomical body, we can infer its distance. Hubble, observing the apparent luminosity of these Cepheids in the Andromeda Nebula and estimating the absolute luminosity from the periods, could immediately calculate their distance and hence the distance of the Andromeda Nebula, using the simple rule that apparent luminosity is proportional to the absolute luminosity and inversely proportional to the square of the distance. His conclusion was that the Andromeda Nebula is at a distance of 900,000 light years or more, than 10 times farther than the most distant known objects in our own galaxy. Several recalibrations of the Cepheid period luminosity relation by Walter Baade and others have by now increased the distance of the Andromeda Nebula to over 2 million light years. But the conclusion was already clear. Relations between redshift and distance shown opposite are bright galaxies in 5 galaxy clusters. Together with the spectra. The spectra of the galaxies are the long horizontal white smears crossed with a few short dark vertical lines. Each position along these spectra corresponds to light from the galaxy with a definite wavelength. The dark vertical lines arise from absorption of light within the atmospheres of stars in these galaxies. The bright vertical lines above and below each galaxy spectrum are merely standard comparison spectra superimposed on the spectrum of the galaxy to aid in determining wavelengths. The arrows below each spectrum indicate the shift of two specific absorption lines, the H and K lines of calcium, from their normal position towards the right red end of the spectrum if interpreted as a Doppler effect. The red shift of these absorption lines indicates a velocity ranging from 1200 kilometers per second for the Virgo cluster galaxy to 61,000 kilometers per second for the Hydra cluster. With a red shift proportional to distance, this indicates that these galaxies are at successively greater distances. The distances given here are computed with a Hubble constant of 15.3 kilometers per second per million light years. This interpretation is confirmed by the fact that the galaxies appear progressively smaller and dimmer with increasing redshift. Hale Observatory's photograph. In 1923, the Andromeda Nebula and the thousands of similar nebulae are galaxies like our own, filling the universe to great distances in all directions. Even before the extragalactic nature of the nebulae had been settled, astronomers had to be able to identify lines in the spectrum with known lines in familiar atomic spectra. However, it was discovered in the decade 1910 to 20 by Vesto Melvin Slipher of the Lowell Observatory that the spectral lines of many nebulae are shifted slightly to the red or blue. These shifts were immediately interpreted as due to a Doppler effect, indicating that the nebulae are moving away from or towards the Earth. For instance, the Andromeda Nebula was found to be moving towards the Earth at about 300 kilometers per second, while the more distant cluster of galaxies in the constellation of Virgo were found to be moving away from the Earth at about 1,000 kilometers per second. At first, it was thought that these might be merely relative velocities, reflecting a motion for our own solar system towards some galaxies and away from others. However, this explanation became untenable as more and more of the larger spectral shifts were discovered.